Let's look at the sampling distribution of a proportion. And let's take this example of the 2018 gubernatorial election in Oregon. Gubernatorial, of course, is a fancy word for the governor's election. The two nominees, well, from the two major parties, there were many nominees, but Kate Brown was the Democratic nominee for governor and Newt Bueller was the Republican nominee. And when all the votes were counted, Kate Brown ended up winning with 50.1% of the vote. So we can pretend we take a random sample of n people who voted in that election. And from that random sample, we could calculate the proportion or percent who voted for Kate Brown. So the notation here gets pretty important. P, lowercase p, is the proportion of all voters who voted for Kate Brown. And we know that is 0.501 as a decimal. But p hat is the proportion of people in our sample who voted for Kate Brown, out of that n people, that is. And so p hat is a random variable. It varies from sample to sample. And let's look at exactly what we mean by that. So here I took random samples of size 4,106. So pretend we had some way of selecting completely at random 4,106 people who voted in the 2018 gubernatorial election. And now pretend that we don't just take one sample, we do this over and over and over again. So in our first sample, we found that 2,087 people voted for Kate Brown, which is a total of 50.828%. And we just kept doing this. In the second one, a little lower, 2,055, which was 40.049%. And keep in mind, the percent of all people was 50.1%. So sometimes these are a little higher, sometimes a little lower. Number of people is sometimes higher or lower, but we don't know how many is exactly 50.1% unless we calculated it. So I did this 1,000 times, 1,000 different random samples of 4,106 people each, and you make a distribution. So the number of people who voted for Kate Brown, if we look at this here, that is a binomial random variable. We had 4,106 trials, and what am I trying to say? 4,106 trials, probability of success, in quotes, would be the person voted for Kate Brown. Failure would be they voted for someone else. So this random variable has a mean of mu times p. You can see it is approximately normal, as we saw in the video, our last video from module 5 on gaming. And the standard deviation is given by this formula, square root of n times p times 1 minus p. So if you make a histogram of those results, it looks approximately normal. The center would be at n times p. The standard deviation would be given this formula, which is about this many people. But we could do the same thing and just look at the percent of people who voted for Kate Brown, or proportion, whichever word you prefer. They're slightly different mathematically, but it doesn't really matter for this class. But so p hat is the proportion of people who voted for Kate Brown. Well, so if x was the number of people and p hat is the proportion, how do you get the proportion? You just divide the number of people by your sample size, n. So p hat is a binomial random variable divided by n. So we can come up with these formulas. The mean is going to be p. In other words, the average of all our samples is 50.1%, which Excel's scaling here makes it a little tough to tell, but you can see that's roughly the center of this normal-ish looking curve here is 50.1%. But there's a standard deviation about that too, given by this formula. So the standard deviation tells you how much your samples could differ. So we know that overall 50.1% of people voted for Kate Brown. So if you take a random sample, you expect your sample to be close to that, but it could be a little higher or a little lower given by a normal curve with this standard deviation. In the next in the next video, we'll look at a couple examples where we use this formula.